I would like to welcome everyone. It's good to see so many old names, new names here in this webinar. So my name is Carlos Rivera. I'm the Global Product Specialist for FEFLOW and the Product Owner for FEFLOW. I'm located in Berlin, in Germany. And today it's a pleasure for me to introduce you to some of these new features of this release MIC 2022, meaning the release of FEFLOW 7.5. Okay, so I think it's always good to get started, to having an overview of what has been done in the past. We have so FEFLOW exists for those new in the participants, and also new in the softwares, exists in the late 70s, and we have been developing the software entirely. And in the last years, as you can see here in this timetable, so we have been having releases in a yearly base. Typically, we have 2 releases per year, so minor release in Q1, so end of March, beginning of April, and 1 major release normally coming in the end of November, beginning of December, like the case of this year with FEFLOW 7.5. So we focus in this release in 5 very interesting development concepts, I will call it, because there are different features associated to these blocks of developments. We will talk about conceptual modeling, so how we are changing the way of operating FEFLOW. Numerics, usability is a set of multiple small features making your life groundwater model easier and more productive. FEFLOW and FePEST. So we have a huge updates and change of FePEST graphical interface for parameter estimation and uncertainty quantification. And we also have done quite a good of work related to surface water and groundwater interactions. But let us start. So in case you have questions, you can always write this question. There is a chat window and also a QA panel in Zoom. You can just type your questions. After I finish the presentation, I will start answering some questions. Then we have a live demo, and at the end, I will take more questions if needed. So introducing a workflow simplification. This is the sentence that I would like to use to explain you what is coming in the software now and how it's going to be, what are the next developments after 7.5. So we introduce some approach of conceptual modeling, or we start doing something on that direction at the beginning of the version 7, when we try to connect more closely 3D geological softwares with FEFLOW. Normally, the case is that you do a lot of effort, you apply a lot of effort to set up your 3D geology, and you need to migrate this into FEFLOW, into groundwater or hydrogeological model. Sometimes you need to simplify the numerical model because of the mesh, so because of other type of processes. So we create a workflow to import meshes and also to generate a mesh using 3D geological information. Of course, there are some bottlenecks, as everyone will know here, but that's the intention. If we look today, our workflow is what we have here. So normally you will build a super mesh. It's the location where you will put all your different geometries, so polygons, lines, points, so all the data, all the geometrical data that is relevant to build a mesh, and then come out to an analysis of your different processes that you want to model. You have a mesh, you parameterize, you run the model, and then you do some results analysis. And of course, here also comes a part of uncertainty analysis and model calibration. But of course, there are some limitations in this workflow, and the major limitation is actually here highlighted in red. In case you need to update the geometry, the input geometry before you generate a mesh, it becomes a bit tedious, complicated. So it's doable in some cases with some additional workflows, but it takes a little bit more time, as it's expected, especially for new users. So we came to an internal discussion in the way how we can improve the whole software, make it faster in terms of calculation, but also in terms of workflows. How do you build your groundwater model with FEFLOW? And we have a long-term vision, which in simple words is explained, try to postpone the meshing process late as possible. So we will end up with a FEFLOW version where we have a super mesh. When you provide all geometrical information, you parameterize all the data into your super mesh, so you don't need to have a mesh here. So that is the idea that we are trying to develop. You generate a mesh, run the simulations, and do the next steps. This means that if you need to actually update something in the geometry of the mesh, like extend the area, the modeling area, it could be simply done because the parameters are still connected to the super mesh. So you don't need to reassign information from one or to the other regions. And of course, there is a need for doing this. And the focus is that we want you to concentrate really more on the concepts, on the hydrological concepts, and spend less time meshing. I know meshing is fun, but sometimes it takes some time. So we can try to control this. It's also offer a faster way of updating groundwater models, existing FEFLOW models. And the way how we start developing this is implementing a concept called parameter lookup table. This parameter lookup table, you can see it as a database. All of us has done one or couple of models with some material information. So we all know what could be the conductivity of this type of material. So we end up having databases in Excel or in somewhere else. So you can now put this information into FEFLOW. Of course, the first time you need to populate this database, so you can do it manually or by scripts. But then when you have it, you can reuse it in multiple projects. That's the benefit. And the idea behind is that you can just select any part, any region of the domain, because we are talking about material properties, and connect these regions to a specific material from this database. You have the flexibility here to add many materials as you want, link it directly to the super mesh. This means that when you generate a mesh, FEFLOW will maintain this as will create an association between the resulting element ID after the meshing process and the parameter ID or the material ID available in the database. So you can go back and forward as many times as you want, and every time that you generate a mesh, FEFLOW is going to populate the parameters of conductivity or any material property that you are linking in this database. Of course, this means a lot of gain in the way how we are doing the thing. So it requires, first of all, a initial preparation of the database, but when it's done, once it's actually very simple to use it for the next project, especially if you are working with the same kind of information or using literature information, for example, to define specific values of conductivity, etc. In terms of numerics, there's also a lot of work we spend this year on that because we want to make the software faster, to calculate faster. And there are two streams how we can do that. The first one is focusing on the solvers, strictly on the solvers. And the second stream is focusing on solving the equations, solving the physical property problems in a different way, maybe in an easy way, in a simplified way, in a smarter way. So you call it as you want. So here we are looking in the software side. We have increase of a new version of SNG. So SNG is a very popular library solver package in FEFLOW developed by the Fraunhofer Institute in Germany. They come out with a version 2020, which has some improvements of parallelizations. Of course, we want to have this version in FEFLOW, so it's available for you. We introduce a new solver library package called PETC. PETC is a very famous library for numerical calculations, used for many industries where numerical calculations are required. PETC comes with a bunch of multiple solvers. So you have ANG solver equivalent to SMG. You have also some space method solvers called Krylov subspace methods. The motivation of using PETC is, first, is famous. Second, it gives us additional solvers at one. Third, we have the possibility to incorporate GPU acceleration in FEFLOW calculations. FEFLOW supports GPU acceleration by CUDA devices, so you will need NVIDIA graphic card for this. There is already some gain in the performance for some specific problems, but the major gain in performance using GPU acceleration is really going to come in the next months with the release 2022.1. The reason of that is because, unfortunately, a few days before the release, so it came a new update of the library who is having the fully GPU acceleration for the algebraic multi-grid version of FEFLOW, but it was a bit too late to include it in the release version of FEFLOW. Multiple error norms, so we have also changed the way how error norms and tolerance are handled in FEFLOW, and we have some improvements of speed for specific models, which is something really good to hear. As you know, so there are FEFLOW works with the error tolerance, error norm type. We always, since the beginning of the software, again from the late 70s, we have one single error norm for all the multiple problem classes, flow, mass, and heat, which is okay, has been working, operating, but there are some situations where you need to really separate this error norm for different physics, especially because the normalization being using behind use the maximum occurring value of heat or mass concentration or temperature if you are doing geothermal applications, which could change several orders of magnitude depending on the case. So it makes sense to separate this. We offer now an advanced parameter section where you can just activate this, and then you will have access, depending on the problem class, to a specific error tolerance and error norm, so you can swap between error norms. So I see here in the list of participants some people working with geothermal applications. So normally what we do in these cases is we reduce the error tolerance quite small to have a good convergence in the Borel heat exchangers in FEFLOW. So you can do now have a easy convergence criteria for the flow, but a strict one for the heat, so that you will end up with different time steps and also will improve the convergence of the whole problem of one piece. We also review the way how we calculate velocities in FEFLOW for specific cases with boundary condition constraints and also multi-layer wells and discrete features. There were some things redone and review and improved, so we end up having a speed gain in the performance of the calculation. So I took one of my test cases a bit. It's a big one, I would say. 3.6 million elements is a density-dependent flow mass transport, one species associated to the density. You see in 7.5 we have 1,600 seconds. This one is 6,200 something seconds in 7.4. So you will expect to get again about a factor of 3 or 4. Larger the problem is, the gain is better because we reduce some loops that we are doing for the velocity calculation. So every time that you have more elements, that will increase significantly. So this is good news. So you don't need to change anything in the solver, just need to install 7.5 and you will see this. In terms of usability, we implement multiple small things to make your life easier. So the first block of development is associated to the selection management. So everyone working with FEFLOW knows selections are nice to have, but could be also pain because there are you can really end up with many selections, especially nowadays that you can create your selections with Python, so you can have hundreds of selections in some cases. And sometimes it's easy to lose the overview of this list. So we have a way now to group the selections, so I can have my selections associated to boundary conditions and just group them and call it boundaries. You have a sorting mechanism, so you can just drag and drop the selection, so you can put always the more important for you on the top list, for example. We can have operations done previously per individual selection, now applied at the group level. The classical one is the budget history charting, so you want to create a rate budget, a fluid period budget for the boundaries. Normally until 7.4 you will do right click, activate the switch, then right click, and so on until you finish your 100 selections. So now you can do everything with one single click. at the group level and say all these elections should be budgeted in history. The same is also applicable for the content analysis. And you also get a nice visual feedback to highlight those elections being used for content analysis C or for budget calculations B. For those working in the geothermal sector, we also extend a little bit the Borger heat exchanger, having a new input for energy units. So you have something called energy demand in kilowatts hour. So this could be a constant kilowatt hour. For example, the demand for 1 year, so will be a 6,000 kilowatts per hour for 1 year. Or you can have a time series where this demand changes. So FEFLOW automatically calculates the delta T and calculate using the kilowatts hour and delta T what is the power to be applied for the Borger heat exchanger. And we keep seeing a lot of interest in FEFLOW, Python, C++, open programming interface. So this is also in our heart and core of the FEFLOW development. So we continue improving this to extend the concept of the parameter lookup table or the conceptual modeling in FEFLOW. We also have special APIs dedicated to this. I am going to show in the live demo how you can manipulate these APIs. So you can easily control your database, your entries, everything that you want to do with these APIs. They're really handy. We also have methods now to control the multi-threading in Python. So before you can say start document and FEFLOW will run with a maximum number of threads. You can now control it easily with a simple command or arguments in Python. Since we start adding more solvers into the FEFLOW GUI, we thought it makes sense to have a switch to swap between solvers. You can have a minus solver in your FEFLOW batch run, and you can switch between PADISO to SMG or to PETC ANG solver. It's really, really simple and handy. We will also extend a little bit more this function that you can also control arguments associated to the solver. This is something that we require quite a lot when we do a lot of this numerical benchmarking here internally for our developing purposes. FePEST, I would like to say a few things about FePEST. Not too much, because we will have next week a separate webinar only dedicated to FePEST. The great news for you is that FePEST comes with a new package called PEST++. PEST++ is the successor of the very famous PEST developed by John Doherty in Watermark's Numerical Computing in Australia. It's a really famous software for environmental calculations or inverse problems cases. So we introduced PEST++ first because we want to keep the technology to be the state-of-the-art technology. And second, because PEST++ comes with a very powerful package called Iterative Ensemble Smoother, PEST++ IES. PEST++ IES does the typical job that you could do before with PEST with multiple scripts and runs in one single job, which is history matching, so calibration, and uncertainty quantification in one single run on one single PEST problem. It requires less number of model runs for FEFLOW compared to the classical PEST. As a user, you still have the flexibility to choose between PEST, classical PEST, and PEST++ from your FePEST graphical interface. Depending on the package that you choose, you will have multiple operation options here available, like the ensemble smoothing. Estimation is using the GLM method in PEST++, which is supposed to be equivalent to the classical PEST estimation runs before. So we use this to test it with some real case. So this is a mining case. So it's a 3D model. We have some cross sections here where we have the changes of the different geometry. So we have done quite a lot of pilot point parameterization here. So we have a good number of pilot points, 150 pilot points, conductivities being estimated, transient heads with different weights. Prediction, we estimate what is the dewatering of the whole volume in the 20 years of mine plan. Use PEST IES with 150 samples. So what it does is you give some knowledge about the uncertainty of the parameters. For example, giving a covariance matrix of You can say my parameters are normally distributed with this range, so I'm just giving some standard deviations here. And the outcome of this exercise is everything controllable and visible in the FePEST graphical interface. So we have a lot of GUI components to really make the way to understand and also quantify the uncertainty in an easy manner, because it's really a lot of information through these different runs. So what you will see in FePEST is, in this case, we see the values, so the fluid period values. So this is volumes, negative is outflow in cubic meters, 20 years. So we have gray lines corresponding to each of the samples, the random sample, you have the base model, and there is also a mean value that you can use for understanding some trends. And of course, FePEST also will give you some histograms for each of the individual observations that you attach to the PEST problem. So you can look heads or flow rates or any other type of information that you want to. So I will give more details about this in the next week webinar. Many of you also have been waiting a lot about this groundwater and surface water interaction. Before I go to the technical details, so it's worth it to emphasize something that we are just promoting now. So compared to other mic software of the software package family in DHI, so we are aligning to the same concept to the other mic software. So for those customers who has a valid CERMIT maintenance agreement, so support and agreement, this annual agreement, you will get access to custom features. So for now, we have 2 features. We will start adding more features in the next developments. And now is you are getting a new, for free, included with your license of FEFLOW 7.5, a new version of the hydromechanical plugin, the version 2.0. We are also introducing a new way to do hydrodynamical coupling using the new engine of surface water modeling in DHI called My1D engine. In terms of surface water and groundwater interaction in 1D, so what is happening now is that you can build your surface water model in MyPlus, for example, or in the format MyHydro, or if you have even your old My11 file, this file can be directly imported into FEFLOW. It's quite easy. Just import your file depending on the type of file that you have. It's really flexible. FEFLOW will convert on the flights and update the settings to the new engine called My1D and export a My1DX file. And the coupling will happen through the fluid transfer BC boundary conditions. So it will identify on the fly what is your river network, what is your set of nodes associated to fluid transfer BC. Will do a mapping using some neighborhood relationship and update the values of fluxes or heads depending on the exchange between surface water and groundwater. And obviously, this is replacing the former IFN Mach11 plugin. And the reason is because also in DHI, we are promoting more our My1D engine. So because of development reasons, My1D has a better parallelization, has a better interface compared to the old Mic 0. So you can use My1D in MyPlus, and it's more handy to use, obviously. MyXi and FEFLOW, they are getting closer together with this development. So we have now the possibility to import DSF2 files into FEFLOW. DSF2 files are typically results of MyXi. For example, a common case is the estimation of recharge, so what is being recharged into the saturated zone, but it's not really strictly to this. You could have any other quantity from MyXi that you can put it in FEFLOW. So we have been discussing in the 2 days early webinar with one participants, and came the idea maybe could be a case of water quality. Maybe it could be leakage of nitrates in irrigation or agricultural zones. So MyXi can do quite well all this vegetation stuff. So we can also get these nitrate infiltrations or percolations, and then use it later in FEFLOW for a calculation. So this is a one-way coupling. So you do once in MyXi, export your information and put it in FEFLOW, and you rerun that in FEFLOW. putting this MySheet information as a boundary condition. In this example, will be a sourcing or could be an inlet from top bottom parameter in FEFLOW. We test this with a project here in Germany. For those located in Germany, you might recognize the area. So we have a model in MySheet estimating groundwater recharge. This is the interface in FEFLOW. You import your DSF2 file. You have the possibility nicely to say a reference day and time, so we can get rid of some data that we don't need from the MySheet file. You have two ways how to import this data. It could be point data or polygonal or cell data is named here. And depending on the way how you decided the spatial data representation, FEFLOW will offer you some additional regionalization method. So we implement also area weighted projection so that we can maintain the total integral of, in this case, of the groundwater recharge in the values being assigned in FEFLOW. And of course, the import is spatial and also temporal. So you can really see different spatial variabilities of recharge, this example in wet season, dry season, and how it's changing each of the FEFLOW elements. It's a cool thing. And arriving to the end of this presentation, before we move to the questions and live demonstration, just to remind you, we are having a webinar next week on the 7th of December, 2 times, 7 a.m. and 4 p.m. UTC times. Again, the webinar is free accessible. You can just register. And we are also having some videos explaining the concept of this conceptual modeling or uncertainty quantification. This presentation will be shared, as well the recording of this webinar will be shared with you in 2 days' time. My colleagues from the academy need to post-process this video, and then you will get a copy of this. So let's see questions. Yeah, Stefan. Stefan, the conceptual model approach is really a step forward. Congrats. My question on this is the workflow 3D fit. Yes. So is what I'm going to show you in the live demonstration. You basically need to have elemental selections if you have a 3D model existing, or if you create your elemental selections. You need to link your material regions, and then you can do everything what is possible now in 2D, what I will show in the live demonstration with your 3D model. For the 3D and structure mesh, we still need to complete part of the workflow, but this is going to come in the next 2 months. Okay, so let me start sharing again my screen. I need to see the right screen. I have prepared a simple exercise or demonstration exercise for you. This is the graphical interface. In case you don't know, FEFLOW is already released, so you can go to our website, MyPower by DHI, and download immediately FEFLOW 7.5. There is also update of the plugins by Chem, by Freeze. The PEST utility is also updated because we require the installation of PEST++. So this is the interface in 7.5. So it looks like it didn't change much, but we are going to see some of these changes during the live demonstration. So first thing that I will show you is if I select this polygon and I go to the meshing panel, you will see an entry called material and a value being undefined. So here is the way how you will connect your information about materials to your super mesh. At this point, we do not have any materials, so we need to create these materials. And for this, you go to the edit problem settings. Before you start creating your materials, it's recommended that you define your problem class. This is also new. At this level, you could also say, I would like to have a mass transport or heat transport transient. And why you need to do that is because the table of parameters that you were going to create is for the first time, only for the first time, depends on these combinations of problem class and settings. So I'm just going to leave it as it is. It's unconfined and 2D horizontal. I go to the parameter lookup table. I will add one row. This could be my material. Let's call this sand. I can add the next one, F2, no, sorry, F2. You can call it clay, and so on. You can have this list. You saw my PowerPoint, the list can be really long. You can do it manually, but there are many easier ways to do it with Python. It just takes a couple of lines. And after that, you need to define a material. I would like to set conductivity, and you can put the conductivity that you want. And just put some numbers to make it fast. Two, you can have many parameters, so parameters for the flow, mass, and heat. And when you have your table ready, you are able to start linking. Of course, we're in live, so we need to save some time. So I have prepared already a super mesh with this table. I should have shown you something. I could have imported the file. You can also import the file directly here. It's an XML file, and then you can add the table. So my database contains 7 materials: gravel, medial, sand, until limestone, with conductivities and drain and fillable porosities. Now I'm ready to start defining the concepts that I want to model. So I would say this polygon here is a medium sand. So I have a medium sand here defined. If this is gravel, you need to choose here from the list gravel. It's already done. So I have done all this. This is fine sand, silt, till, etc. So I guess you follow me the concept here. If I press generate mesh, FEFLOW understand that you have created a link between the elements that before they do not exist with the material region. And these elements, or this connection, is stored in material region. So now I have my gravel, sand, fine sand, and so on. It knows that I have conductivity values associated, and also knows that I have a drain and fillable porosity. So I can go back every time to the super mesh. I will close the super mesh. Now, the project manager said we need to extend the modeling area to this location. So let's say we extend this, and I only need to assign this new area a material. This will be this time silt. Enter, and then remesh or mesh again. The mesh is below. I have materials, nothing outside change. This area is now become silt. Very fast. Conductivity and drain and fillable porosity is still there. Other way to use it, this is through the for the assignment. So let's say we are going to set some recharge to some irrigation areas. So I will go back to my problem settings. I don't have the parameter sourcing. I will easily, sorry, I need to add a parameter. This parameter will be sourcing for the fluid. Because of time, I will just give some values. So I say the gravel will have 0.01. Then apply. Immediately, gravel will get this value. I will say this one. So let's do some negative. So it's going to create some outflow. Apply, and I immediately assign medium sand this value here. This will be 0, 1, 2, 1, 2, 3. So numbers 4, 5. Apply, and each of the zones will get. So probably because of the scale, we don't see, but the values are being assigned actually over the entire model domain. So it's really easy to modify this. Also nice, if you change the problem to transient, apply, and go back to the parameter lookup table, you could already assign your time series at this level. So if in the past it was quite complex or tedious to assign these material stages to conductivity or recharge, now you can do it one single click for this specific region. All right, so So what is also very important to know is that if I look now, let's say I need to modify the mesh. I have to put more elements here because of a specific region. So I can just go and say mesh refine elements. So FEFLOW will keep obviously bookmarking of the region. So every new element has get the same conductivity. So every mesh operation will update the values as they are connected to the material regions. You still are flexible to do the operations as done before. So you can import your maps, do link to parameter, interpolate, or do constant sum assignment with polygons. So these workflows are still there and will be always available for you. Other way to do that is through Python. So we can say now that I will open my edit script here, and again we are live, so I have prepared some lines of Python. So I would like to get the overview of this table. So I can just have 2 lines of code. One to get is a new parameter or new type of object called lookup table. And I see it's a bit small, but you will see here gravel 1, medium sand 2, and so on. And the number is the ID of the material. Let us now let us find if there is a value in the database called clay. I print, let me close this, clear this, print this. Of course, there is an error because I forgot I delete the upper part. So I need to initialize the object first. Clear, and then if I print it, so there is a delete this one to see more things. Then you will see here the line for clay. 100 is the ID of the material property. 100 stands for conductivity, and then you have drain and fillable porosity and a value of sourcing. You can also change the parameters. You can say, let me now change the override the parameter of conductivity to something else. So I will say I would like to override the value with this line to 10 to the minus 6. So I can just do that, and then I ask again, give me the conductivity of clay is 10 to the minus 6. Okay. If I go to the database or the parameter, okay, that is in meters per second, we can change, but it has changed actually. And the conductivity, we can look clay. What is the? I think I don't have clay here, but I can select and choose here a clay. This is clay. This area is clay. And if I look, the conductivity was in meters per day default, 10 to the minus 6 meters per day, you see in the upper right screen. Okay, what else? So you can see here from the numerical parameters, the option for the error node. So you can switch this and activate these options in terms of the equation system solver. You see the new solvers, FEFLOW with an Krylov subspace solvers. You have also ANG method. If you choose FEFLOW, apply, and then you go to properties, you will see here an option. In my case, it's gray out because I don't have a GPU supporting graphics card, CUDA graphics card in my laptop here at home. But this option will be active if you have an NVIDIA with support of CUDA, so that you can use this GPU acceleration. In case you want to do the coupling with my 1D, is this one, hydrodynamics. Then you have the new tab in FEFLOW where you can import your river setup, and this setup is the only information required, and you need to control the times. So all the rest of the mapping between nodes and river networks, edge grid points from my 1D are done on the fly in FEFLOW. Selections, so we could nicely create a couple of selections here. So let me call this selection 1. Then this one will be selection 2. I can simply select the groups and then say they belong to the same, and these are my selections. I would like to compute the fluid budgets in each of the selections, so I can just do a right click and say content history charting fluid volume, and comes a C. The same is also applicable for nodal selection. You could group in and all the other selection types, obviously, as well. And for the import of DSF2 files, you do a right click on the maps panel, and you have the possibility to just simply choose the import file, DSF2 files here, and then you can import the file, and FEFLOW will guide you through the whole process. Thank you for participating in this webinar, and I hope you enjoy the new version of FEFLOW 7.5. I'm confident that there is quite a number of improvements in terms of workflows and in terms of calculations. So just take it, give it a try, download it, and I will be also happy to hear your feedback. So if you like it, the way how we are doing this, so the way how we plan to develop now, so there is still a lot to come with this conceptual modeling. So it's really now the peak of the iceberg that we start developing. We need to implement more methods, for example, for generating wells or doing interpolation at the super mesh level. So we want to have most of this information mesh independent, so that we can minimize the efforts on the bottlenecks by generating meshes later. But that is going to come really soon in the next month. So you know what is the vision of the software in terms of solvers. So we keep working with PET-C and inject GPU parallelizations at maximum. Okay, so that's it from my side. Thank you for participating, and until the next time. Have a nice evening or nice day for those just starting. Bye.